All right, so we just finished the groundwater with Dave, and now we're going to move on to structural elements. So soil and rock structural interaction via structural elements. Okay, so who here has used structural elements in old FLAC or FLAC2D or any other code? Oh, okay. That's totally fine. I don't think I introduced myself formally. So my name is Derek Blanksma. I'm an engineer here at ITASCA. I've been here for about 10 years now. I started as a consultant right out of graduate school from the University of Minnesota. I did the consulting for about 7 years and then switched full-time to development, which it's been more kind of in line with what I like to do, developing. But I also have a lot of background in consulting, so I do keep foot in both worlds. So it kind of gives me the advantage of knowing what the consultants need and what the developers can do. But yeah, so I've been with ITASCA for 10 years now in April. And I primarily developed FLAC2D. And specifically been doing the structural elements, which we're going to talk about. The structural element logic was originally developed back in the 90s by David Potbiondi. I don't know if you guys are familiar with him. Maybe he does the PFC training. So he developed all of it, and I basically ported it over to FLAC2D. Structural elements is one of our kind of bread and butter sides. It's extremely useful for a lot of applications in civil and mining engineering. It kind of sets us apart too from a lot of the other companies because it's we basically have this finite difference code, FLAC, and then you also actually have a finite element code, which is all our structural elements, our finite elements. So there's basically both finite difference and finite elements in the software. But we'll go more into the details as we go through the presentation. So here's a brief overview of how the next 2 hours is going to look. I'm going to talk a little bit about why we develop these structural elements, like why just not use finding differences for everything, just keep it with what we know. I'll talk about the motivation and kind of this bringing the idea of showing you the documentation early in the presentation, just because I use the documentation a lot. And I hope you guys do as well, because the documentation is very extensive, but it's been written very carefully and thought out very well, so people know what they're doing. You know, going into the documentation is a little formidable at first because there's so much, but I use it every single day. It's my the first star in Google. It's going to the my documentation and seeing what's all in there. And I'm sure using the codes, you guys will do the same. And then I'll give a brief intro on the types of structural elements. Basically, in 2D, there's beams, piles, cables, liners. Stays with that. Then we'll look at an example called the fundamental. I call them the fundamental four: the beams, piles, cables, and liners. It's just kind of a toy example, so we can see what they're doing. It's not a real engineering example. Then we'll talk a little bit about the mechanics, keeping that at a minimum, very general. A little bit about the scheme, finite element scheme, and we'll talk a little bit about the stiffness matrices, and we'll go into an example about a uniformly loaded beam, which has an analytical solution that we can compare to. After that, we're going to actually go more in depth about each one of these structural elements, talking a little bit about what it does, what it's used for, how it's different than the other ones. And then after that, we'll talk about coupling. When I say coupling, just remember it's the same as links. It's the same as element grid interaction. Basically, what coupling is how these elements interact with your FLAC2D zones. So that's a very important concept, which I'll try hit home. All right, and then getting down to the end of the presentation, we'll talk about something called 2D, 3D equivalence. Basically, what these 2D models are infinite out-of-plane models if you want a perfect 3D equivalent. And we'll talk a little bit about that because that's a very important concept that it's easy to get wrong when you do a 2D analysis. You think, oh, I'm just modeling one single pile surrounded by soil. That's not the case in 2D. What you're actually modeling is a line of piles that are spaced 1 unit out of the plane. Then we'll talk about more. And then we'll go into a more in-depth example. I think of pile with bearing capacity. It's pretty applicable. And then I'll talk a little bit about some future development for specifically for the structural elements in FLAC2D. So FLAC2D obviously is a new code, so we're still working out a lot of the bugs. So we're still implementing a lot of the stuff that was in FLAC into FLAC2D, and we'll talk a little bit about that. Okay, so the motivation for structural elements. Basically, this is what it boils down to. We really don't absolutely need structural elements in the code. What you can do is model every single thing with zones. So take this tunnel, for example. It might be a little hard to see there, but if you look closely, I actually generated a liner, a shotcrete liner or something. And it turns out that to really model this correctly and represent the response of a structure like a liner, you need a lot of zones through the thickness of it, typically on the order of like 6 or 10. So then you think about that shotcrete, I don't know, maybe it's sprayed on there a couple inches thick. So you're going to have a couple inches of shotcrete modeled with 10 zones thick in a tunnel that's meters upon meters wide. Basically what I'm saying is this is going to create extremely small zones in your model, and typically those zones will be stiffer if it's shotcrete, which all points to this model taking a very long time to run. Anytime you have very stiff zones, very small zones, that all will dominate your time step. So you could be running this model where the time step has to be reduced to a very, very small number, and it takes forever to run. So the way we tackled this problem is we introduced structural elements. So instead of using zones, we idealized the structure as a one-dimensional object. So basically, instead of having an actual thickness, it's a 1D beam that will be substituted here instead, and that will interact with the grid that will bend and yield and take forces like an actual structural element. So if we're not interested in the small scale local effects, so like the stresses or the forces that develop through the thickness of it, we're more interested in the global aspect of the element, how it bends, how it deforms. Then structural elements are an ideal substitute for this. Okay. So like I said, I use the documentation a lot, and I kind of wanted just to point out some important aspects of our documentation before we just dive into coding or the rest of the presentation. So it's kind of ugly. I just kept the whole string of our documentation here, but basically all I'm showing here is that we have a dedicated website that has all our documentation on it. And you can also just bring up that exact same documentation from within the program. So like I said, it's quite extensive. Our entire world right now is going to be right here. So it's I kind of wish they wouldn't have made it like this, but it's all under ITASCA software guide. And the reason we did that is because structural elements are not just specific to FLAC2D. You can use structural elements in PFC. You can use structural elements in 3DEC and UDEC, FLAC3D and FLAC2D. So you can all use those in our other software. That's why when you're like, maybe you're going to that documentation, like, where the heck is all this stuff for structural elements? Just remember, it's the very top one, ITASCA software guide, and then structural elements. An important thing to note, then, a lot of the different element types will be distinguished by 2D and 3D. So 3D obviously has a lot more because FLAC2D is just an extension of 3D, maybe a reduction of 3D, I'll say. So it will tell you which ones are 3D only. Pretty much anything that's a line, like a cable, a beam, a pile, that's all in 2D. Anything that's a plane, out of dimension, out of plane, is going to be 3D only.